In 1905, Einstein showed that Galileo's ship of relativity could safely sail on Maxwell's electromagnetic waves if we assume that the speed of light is constant to all frames of reference. But what precisely does that mean? It means that no matter how fast you are moving relative to the source of a light wave, you will measure the speed of that light wave relative to you at 299,792,458 meters per second. Let's say that you've got a device that can measure the speed of a light beam as it passes you. Let's say you also have a flashlight. Take that flashlight, point it at your device, and it will measure the speed of that light at 299,792,458 meters per second. Now, get onto some railroad tracks. Stand in front of a train as it's barreling down at you at 100 meters per second. Use your device to measure the speed of the light from its headlamp as it's coming towards you, and your device will read 299,792,458 meters per second. Now, jump out of the way as the train passes, then get back on the tracks and measure the speed of the tail light as that train runs away from you at 100 meters per second, and your device will read 299,792,458 meters per second. You can repeat this experiment as often as you like. You can do it in a car, you can do it in a jet plane or a rocket ship. You can use the Earth whipping around the Sun or the Sun plowing through the galaxy. It doesn't matter. Every light beam you measure, regardless of how fast the source of that light beam is moving, will move relative to you at 299,792,458 meters per second. And every other observer who measures those light rays, regardless of how fast they're moving relative to you, will measure them moving at 299,792,458 meters per second relative to them. When a light ray passes you, it's going at 299,792,458 meters per second. No matter what. Now imagine that I have a clock. This clock is constructed out of a tube with mirrors at either end. There's a beam of light bouncing back and forth between the two mirrors. The clock ticks every time the beam of light hits one of the mirrors. If the tube is 12 inches tall, then the clock ticks at a rate of once per nanosecond. Imagine that both you and I have such a clock. You are in one spaceship and I'm in another. We're both moving fast. You're moving towards me. From my point of view, I'm stationary. I look at my clock and it's ticking at 1 tick per nanosecond as usual. But your clock is moving relative to me. The light beam must move at an angle in order to hit the two mirrors. That means the light beam is moving a longer distance. And so your clock ticks slower than mine. You don't see that at all. From your point of view, you're stationary and I'm moving. You look at your clock and you see the light bouncing at 1 tick per nanosecond. But when you look at my clock, you see the light beam moving in that zigzag pattern, taking longer than 1 nanosecond per tick. From my point of view, your clock, and therefore your time, are running slow. From your point of view, my clock and my time are running slow. How slow? Well, by applying the Pythagorean theorem, it's pretty easy to show that I will see your time running slower by a factor of the square root of 1 minus your velocity squared divided by the speed of light squared. This is a factor often called tau. As you fly overhead, I hold up a foot-long ruler parallel to your trajectory. I count the number of ticks that occur on my clock as the nose of your ship passes from one end of the ruler to the other. You do the same, counting the ticks on your clock. But you count fewer ticks than I do, and therefore you believe my ruler is shorter than it actually is by a factor of tau. As we pass each other, our rear stabilizer fins bump into each other ever so slightly, giving us both a nudge in a perpendicular direction. Momentum should be conserved, so when I look at your ship, I should measure your perpendicular velocity equal to mine. But since I perceive your time is running slowly, I see your perpendicular velocity is too slow by a factor of tau. The only conclusion I can come to is that your mass has increased by an identical factor. Remarkable, isn't it? All these counterintuitive effects simply by assuming that the speed of light is constant to all frames of reference. And these effects have been experimentally verified to umpteen decimal places of accuracy. The world is truly a very bizarre place. And we haven't even talked about general relativity yet.